moving on with the rate of change test. So we have a word problem coming up. So a ball is tossed straight up in the air. Its position is modeled by st equals negative 4.9 t squared plus 16t plus 2, where s of t is in meters and time t is in seconds. Find the exact instantaneous rate of change at 2.5 seconds. Find the average rate of change when the time is between 1.5 seconds and 2.5 seconds. And then estimate the instantaneous rate of change at a time of 2 seconds. So part A, we have to find the exact instantaneous rate of change at 2.5 seconds. Keyword here is exact. Only way to find the exact instantaneous rate of change is using the difference quotient. So we got to find the exact instantaneous rate of change at a t-value of 2.5 seconds. So that would be what? We would have to use this function, so it would be s of 2.5 plus h minus s of 2.5 all over h, right? So this is the difference quotient right here. So let's, on the side, simplify these expressions in the numerator. So when we plug them back in here, it's a lot easier. So what's s of 2.5 plus h going to be? So we plug in 2.5 plus h for the t values in the function. So we would have what? Give myself a little room here. So we'd have negative 4.9 times 2.5 plus h squared. And then we're going to plug in this 2.5 plus h for this t here. So we're going to have plus 16, 2.5 plus h, and then we're going to be adding 2. So now what you have to do is you have to simplify all this. So 2.5 plus h squared, that's the same as what? 2.5 plus h times 2.5 plus h. So you're going to have to FOIL all of this out. So 2.5 times 2.5, that gives us what? 6.25. And then we're going to end up having, when you FOIL all this out, you'll end up having 5h plus h squared. So 2.5 plus h squared, that's what the remaining or the simplified expression is going to be. And then we can factor in, distribute that 16 inside the bracket. So 16 times 2.5, that would give us what? 32, that would give us 40, plus 16h, and then we still have this 2 at the end there. So then distributing that negative 4.9 in the bracket, we would end up with negative 30.625 minus 24.5h minus 4.98 squared, and then this portion stays the same, plus 40 plus 16h plus 2. And now at this point we just have to collect like terms. So notice how this negative 4.9h squared, that is a term by itself. This negative 24.5h plus 16h, we can simplify that, and that would give us what? That would give us minus 8.5h. And then the numbers 40 and 2, and then negative 30.625, you net all those out, you end up getting 11.375. So this here is the simplified expression for s of 2.5 plus h. Now we also need s of 2.5, and that's a lot easier than this one because all you have to do is plug in 2.5 for the t values. And if you do that, simplify everything, you would end up getting 11.375. All right, so plugging all of that in to our difference quotient, so s of 2.5 plus h is negative 4.9h squared minus 8.5h plus 11.375. And then we're going to be subtracting s of 2.5, which is 11.375. And this is going to be all over h. Basically, when you're doing the difference quotient, especially with polynomial functions, you get to this point, you want to make sure that the numbers are going to be canceling each other out. right? Because you want to get rid of this h in the denominator, and the only way to do that is to factor out an h. So you can't have any numbers by themselves. So if you get to this point and these numbers aren't the same, the numbers aren't canceling out, you know you did something wrong in this step. You got to go back and look at your algebra. So these numbers are going to cancel out, and we're going to be left with negative 4.9h squared minus 8.5h in the numerator. We can factor out an h from those two terms, and we'd be left with negative 4.9h minus 8.5. It's going to be all over h. Notice how now the h's cancel out, right? And we're left with, I'm going to erase this portion here. So I'm going to continue it up here. So we'll be left, after the h's cancel out, with negative 4.9h minus 8.5. And now to get that exact instantaneous rate of change, we will plug in 0 for h. We want h to be very small, right? So we'd be left with negative 8.5. And now what are the units going to be? S is in meters, T is in seconds, so this is going to be negative 8.5 meters per second. And the reason why it's negative is most likely this ball now is going down. So the way this graph is going to look like is the ball is thrown, and notice when it's thrown at a time of 0, it starts at a position of 2 meters. So we can assume that this position is dealing with height. It's going to get thrown up, and then it's going to come back down. So at 2.5 seconds, the ball is probably somewhere around here. It's going down, hence why we got a negative velocity. So the instantaneous rate of change is negative 8.5 meters per second for part A. And because they asked for the exact instantaneous rate of change, we had to do it this way. We had to use the difference quotient and algebraically manipulate it. Now moving on to part B, a lot easier. Average rate of change when time is between 1.5 seconds, 2.5 seconds. So average rate of change equals S of 2.5 minus S of 1.5 all over 2.5 seconds minus 1.5 seconds. Now S of 2.5, we actually solved that in part A. We know that that's what, 11.375. S of 1/2 though, we didn't do. So what you would do here is you would plug in 1.5 into the function for t. And when you do that, you end up getting 14.975. So that's what S of 1.5 is. So that's the height at a time of 1.5 seconds. And then the denominator, 2.5 seconds minus 1.5 seconds, that's just 1 second. So when you simplify the numerator, you would end up getting negative 3.6 meters up top all over 1 second. That gives you negative 3.6 meters per second. So that there is your average rate of change over this interval between 1.5 seconds and 2.5 seconds. And then finally, part C, we have to estimate the instantaneous rate of change at a t-value of 2 seconds. Keyword in this question, estimate. So we don't have to find the exact, so we don't have to do that whole difference quotient stuff. We can use preceding interval, following interval, centered interval. We've been using a lot of centered intervals, so let's switch up. Let's use the following interval. So we would use 2 seconds, and then we can also use something very close to 2 seconds, but greater than it, so like 2.001 seconds. So if we find the average rate of change between those 2 seconds, because they're very close, that would give us a good approximation for the instantaneous rate of change, or the slope of the tangent at 2 seconds. So instantaneous rate of change, perhaps I'll write approximate. Instantaneous rate of change is what? S of 2.001 minus S of 2 all over 2.001 minus 2. So to find S of 2.001, we would plug in 2.001 for the t values to find its position at that time. So when you plug all of that into the function, you end up getting 14.3963951 for s of 2.01. S of 2 is just going to be 14.4. Going to divide that by 0.001, which is what the denominator simplifies to. Simplify all that in your calculator, you end up getting negative 3.6049 meters per second. So approximately negative 3.6 meters per second, which is the same as the average rate of change that we got from 1.5 seconds to 2.5 seconds. And that sort of makes sense because notice how 2 seconds is in between that interval in part B, 1.5 seconds and 2.5 seconds. So makes sense that it's going to be around there. So this is the approximate instantaneous rate of change at a time of 2 seconds.